Hello and welcome to another video lesson with Lawson. We're going to continue the kinematics unit, trying to understand not only the concepts that relate to motion, but how we can use math to model the motion and then to be able to describe and eventually solve problems related to analyzing motion. We're going to look closer at how position plays a role in describing the motion of an object. There's the obvious math correlations, which is the position is where you're located in the universe relative to that arbitrary origin that we mentioned, depending on your coordinate system. We often use the variable x, although you'll see some references use the variable s, because it might be not only a position along the x-axis, it might be along the y-axis or the z-axis. We could be using a different coordinate system entirely. So if you see an s in a reference, it simply is another way of saying the position instead of aligning it to a specific coordinate system. In this case, we're aligning it to the positive and negative x-axis. We're just simply assuming that if you're only moving in one direction along the line, we might as well make that line the x-axis for ease of description. You'll also see at certain points, instead of referring to it as the xyz plane, we'll refer to it as the ijk plane, the I hat, j hat, k hat, so that when we're describing something moving along the x-axis, we don't say its position in x's, we say its position in I hats. And if we are describing something moving along the y-axis, we don't say its position in terms of y, we say its position in terms of j hat. Again, mathematically, there's the straightforward that the derivative of your position with respect to time is your velocity, and the second derivative of position with respect to time is your acceleration. When we have a graph that represents that function, or if we take a function and we graph it or imagine what the graph of that function looks like, there's a couple of characteristics that come out. If the graph would be a horizontal flat line, then your position is constant, it's not changing. You don't have a change of position over time. That means that your velocity is zero. If your velocity is not changing, then you don't have an acceleration. In each of those cases, a nice horizontal flat line tells us that the position is constant and not changing, and it also tells us that the velocity is zero and the acceleration is zero over that time interval. If we have a position graph that would be a straight line but not horizontal, it would have a constant slope, then the change in position with respect to time, or the slope of that line, is your velocity. And since that velocity would be a constant, your acceleration would be zero. If we have a position graph that has a variable slope, it has a curviness to it, then we know that the velocity is changing with respect to time, so there must be an acceleration taking place. If it's a single smooth curve, then the acceleration is constant. If the curve has some change in how it curves, and often terms you'll refer to that as a change in its concavity, or a change in the rate at which it is changing over time, then we have a non-constant acceleration. In this instance, we're looking at a graph that's described by the function 45. So the position with respect to time is equal to 45 as noted above. When we imagine or look at the graph, it's a horizontal line at the 45 point on the y-axis or on the position axis. So as time goes by, the position doesn't change. We know, since it's a horizontal flat line, the velocity is zero and the acceleration is zero. The position as a function of time is equal to 45. Therefore, if we're trying to get the velocity as a function of time, that's going to equal the derivative of position with respect to time. The derivative of a constant is zero. So we can now see the velocity function as time goes on is zero. And if we want to get the acceleration with respect to time, that's the derivative of the velocity function with respect to time. And since the velocity function is a constant zero, the acceleration function is a constant zero. And we see that mathematically what we anticipated, which was since our position is not changing, we're at rest, our velocity is zero, and since our velocity is not changing, our acceleration is zero. Now we see a position function, where position is a function of time, is equal to 25t. it's not hard to imagine or to be able to tell that every time we put in a new t, the position increases by 25 times that new t's value. And so if we imagine changing time at a 1 second rate, our position is changing at a 25 units rate. When we think about the velocity as a function of time, which is going to be our derivative of position with respect to time, that's a constant times the variable. The derivative of a variable is 1, so this will be that constant times 1, or 25. And we can see that our velocity function is a constant 25, which makes sense since this is a straight line. We expect a constant velocity. If we're looking to see what acceleration as a function of time is, that's the derivative of velocity with respect to time. And since velocity is 25, or a constant, the derivative of a constant is 0. As anticipated, the acceleration is 0. Now we have a position as a function of time described by the function 3t squared plus 4t. Seeing the t squared variable gives us some clue that we expect some kind of parabolic curve. And as we look at the graph of that motion, we notice it is just that. It's an increasing slope. It starts out looking close to 0 and gradually increases until it's not anywhere close to 0. If we're trying to describe the velocity as a function of time, that's going to be the derivative of position with respect to time. 3t squared is a constant times a power. 3 times 2 times t to the second minus 1. 3 times 2 is 6. T to the second minus 1 is t. 4 is a constant, t is a variable. The derivative of a variable is 1. We're adding these two functions together, so we're applying the summation. We're finding the derivative of each separately, then adding them. The derivative of 4t is 4, so this is plus 4. And when we're looking to get the acceleration as a function of time, that's the derivative of velocity with respect to time. Our velocity function is 6t plus 4. Again, we're adding two functions, so we're going to do the summation. 4 is a constant. The derivative of a constant is 0, so we'd be adding 0. We don't have to show that. 6 is a constant times a variable. The derivative of a variable is 1, so t becomes 1, or we see that the acceleration is 6. It's nice when we see a straight line, whether it's horizontal or at an angle. We know for certain it's a constant acceleration, more specifically that the acceleration is 0. It's interesting when we have a curve, like we saw in the last one where it was a smooth curve, the intuition is that the acceleration was constant and we noticed that it was. It's important if we have the function to actually determine what the derivative of velocity is so we can see how acceleration is determined relative to time and see whether it's a constant value or not. In this case, the position as a function of time is described by t cubed minus 6t squared minus t plus 30. So when we're getting the velocity as a function of time, which is going to be our derivative of position with respect to time, again we have a summation or a subtraction, so we're going to do each part separately and then put those pieces together. T cubed is going to be 3 times t squared. 6t squared is going to be minus 12t. T goes to 1 minus 1, and 30 goes to 0. So our velocity as a function of time is equal to 3t squared minus 12t minus 1. If we're looking for our acceleration as a function of time, that's our derivative of velocity with respect to time, or the second derivative of the position with respect to time. We see a similar process here. 3t squared, that's a constant, times a power. That's going to be 6t. 12t is going to be 12, and 1 is going to go to 0. So we see that our acceleration as a function of time is 6t minus 12, or not a constant, which is not surprising because we can tell from the curviness of the graph it's not likely that it would be constant. In this example, the position as a function of time is described by some function of time. We're not actually given the details, we're just told there is a function with respect to time that would describe this position as it changes or as time goes by. What we notice is that in the beginning we have a bit of a curve up. It looks a little bit like the graph we saw not too long ago where our slope is increasing. So our velocity is increasing, then we see it gets a bit of a straight diagonal nature, so our velocity is constant, and then it goes to a horizontal where velocity would be 0, then it increases in the negative direction, so the velocity is decreasing or increasing in the negative direction or going further away from 0 in the negative direction, and then it's got a straight diagonal, so it's a constant negative velocity for the remaining period of time. Since we don't have the actual function, we can only describe it mathematically in terms of those variables. The velocity as a function of time is going to equal the derivative of position with respect to time, which in this case is the first derivative of that function with respect to time. The acceleration with respect to time is going to be the derivative of velocity with respect to time, or the second derivative of that original function in terms of t. What we want to be able to do with a graph like this is be able to identify regions where the velocity is 0, whether it's getting further away from 0 or closer to 0, and where we might have the greatest velocity in terms of magnitude. Where is this object moving the fastest? Where is it having the greatest change in position as a function of time? And what we notice is we start at the origin and we speed up and we move away from the origin, and it took about 10 seconds to get to that maximum displacement away from the origin, and then we stop, and then it looks as though it turns around and speeds back to the origin. So what we notice, it takes about 5 seconds to get from that place where we were resting or stopped and return to the origin. We can tell that the velocity for that final 5 seconds would have to have a much larger magnitude than it did in the first 10 seconds. It turns out, since it's a negative velocity, it's a little bit annoying because a larger negative number is actually a smaller number. Just from a math sense, we would say it's a smaller velocity because a negative number is smaller than a positive number. However, when we talk about the magnitude of the velocity, we would say that it is a greater magnitude because the value that represents the velocity would be larger. Another way of saying that is the absolute value of velocity, which is speed. The absolute value is the magnitude, and since it has a greater magnitude, it would have a greater speed during those final 5 seconds.